And the machine that makes that possible is this one here. This is a TSR electron target. So this is a blow-up. It's a relatively complicated setup. We have a stored ion beam that's circulating on the orbit here. Then we have the electron beam that is produced here. In our target, we have a very special setup here where we produce the electrons not from a cathode, but from a photomaterial that we illuminate with a laser and use the photo effect. That way the electrons are much colder to begin with. And then they're slowly accelerated adiabatically. They're guided by magnetic fields to superimpose to the molecular ion beam, and then we take them out again and collect them in the collector section here. If we have molecular breakup here and neutral products, they will just not be impressed by the magnetic fields anymore, fly straight ahead, and we can collect them here. And for atomic ions, typically the charge state is lower than previously, and then we can collect them here. And this machine is designed to produce a very monoenergetic electron beam that can reach resolutions to below milli-electron volts. So what can we do with that? This is a classic example here, a relatively old publication, 1997, where people looked at iron 17 plus, they're combining with an electron. But you can see here, all these peaks here are the product of this dielectronic combination, where we have a resonant process we capture into a shell of the atom, and the energy is very well defined. You can see that we have a very good resolution. We can see all these different N states here, and we can also see some smaller peaks, which are the different L peaks that we can also see in the experiment. Radiative recombination would be hidden here. It typically peaks around 0 eV, and it's typically lower than the highest peaks here. The dielectronic recombination is faster by an order of magnitude or 2 than the radiative recombination typically. Don't pin me down on those numbers. So it's typically hidden in this peak at 10 to the minus 11 cubic centimeter per second here. Now this is kind of a standard measurement. Now, in the meantime, with this new electron target, by this group of people here, a much better resolution can be achieved. Here you can see electron recombination measurements in scandium 18 plus that were measured at very low detuning energy here. And in principle, one should see 3 resonances here, because there are 3 states that you can couple into. But one sees more than 3 peaks, and that is because one can actually see now the hyperfine splitting of the energy of the electron in the lower state that is lifted up in this process here. So that is a relatively new achievement. With this target, we really have a great resolution that we can also apply to molecular experiments. Okay, going from atoms to molecules, it turns out that the situation gets much more complicated, both for us experimentalists as well as for theoreticians, of course, because we have much more possibilities now. If we have a molecular ion recombining with an electron, we have to worry about the excitation of the fragments. If we have molecules there, we have to worry about maybe electronic excitation of the fragments, different kinetic energy releases in different channels. But for us experimentalists, one of the biggest problems is that we have to prepare this molecular ion with a known internally excited state. That is always one of the larger problems that we have there. So the relevant parameters we have to worry about are the absolute reaction rate coefficient. That's often something we want to determine. The internal excitation of the initial ion is a very important parameter. The branching ratios of the different product channels, the excitation of the products, and the dissociation dynamics if we get to that. Now here's a benchmark measurement. This is the Hd plus ion. This is an ion that's often used as a proxy for H2. The advantage is that it's infrared active. It has a dipole moment. That means it cools in our storage rings, while H2, if we inject it internally excited, it will just stay there and sit there. Nothing will happen because it doesn't have a dipole moment. And this is a comparison between these 3 storage rings that has been done a couple of years ago. You can see the rate coefficient that has been measured at all 3 storage rings, offset by a little bit so that one can see it better. You can see that the rate coefficient looks similar with all 3 of them, except for that they have different resolutions. Astrophysics didn't really have a cooled electron beam, and the best one at that time was cryo here with a 2 millieV resolution. But the overall agreement, also on an absolute scale, was very good. Now for Hd+, the electron recombination happens mainly through this direct process by a dissociative state that crosses all the ionic states here at low energy. And of course it has different overlap with these vibrational states, therefore one can worry whether, or can ask oneself, what happens with vibrationally excited ions. And at the TSR we have a unique instrument that we can use to do in situ diagnostics of the vibrational states of molecular ions. That is called the Coulomb explosion setup, where we can extract a small fraction of the ions while they're circling in the storage ring at a thin foil here and guide it into a dedicated beamline, where we shoot it through a very thin target foil. Because we have mega electron volt energies, the electrons are stripped off immediately in that foil, while the nuclei come out more or less unperturbed, and then they dissociate because of their mutual Coulomb repulsion, and we can measure the distance here on the detector. We can measure it in all 3 dimensions actually, and really reconstruct the molecular wave function. So what we can do is we can shoot in vibrationally excited ions and then watch them cool by looking at the vibrational wave function that has been done in a beautiful experiment here with HD+. Before I joined the group, where you can see the molecular wave function here for the first 10 milliseconds of storage, 50 milliseconds, and then eventually where we have V equals 0 and 100% after about half a second. So one can really see the vibrations cooling inside the storage ring, and one can also use that to extract, to follow the vibrational states here in the first few hundred milliseconds, and then extract vibrational state specific rate coefficients for different V states here. Okay, that has all been done a while ago. The state of the art now is that we're looking at really low collision energies with high resolution. This is a comparison to a theory that is done by Johann Schneider and co-workers. So what you see here are the TSR data, the most recent ones, with different peaks at very high, very low energy here. And now we start actually plotting stuff on a linear scale. Usually all these plots were a doubly logarithmic scale. But now if you look at the details, we're plotting it on a linear scale. This is the so-called reduced rate coefficient that's multiplied with velocity to get the intrinsic fall-off out. And what you can see here is that it doesn't actually look too bad. The 300 Kelvin theory that we have here, at least for this peak here, we see a clear correspondence, and then some of the other peaks may be there, but at very low energy, we can't really claim that the agreement is perfect. And the question as of now is that do we have an experimental issue, or is it still an issue of the theory to reproduce those? And therefore, we would, in the near future, like to go away from 300 Kelvin. That's where our storage limits us, and see if we can get this picture even a little clearer. So here you can also see the single rotational levels that contribute. If one could get down to J equals 0, J equals 1, then maybe we could get a clearer picture. Okay, now I want to switch to the simplest polyatomic ion, my favorite molecule, H3+, is a triangular molecule that is one of the key ions in interstellar space. It's a very active proton donor. It creates much larger molecules as a catalyst in a sense, and it's a very important molecule in the interstellar medium. Also, the dissociative recombination of H3+ is very important. It's one of the more important parameters in interstellar cloud models, and therefore it has been measured more than 30 times, and there are more than 30 published rate coefficients for this little reaction here. Unfortunately, pretty much, I think 2 or 3 of them agree. All the others range over 4 orders of magnitude, and if you have a group of experimentalists that all measured the same thing, they all have different results. It makes for very lively conference. We have looked at this process with all the means that we have available at Heidelberg. So here I dive right into it. I don't want to tell you all this history and the controversies. This is what happens if you plot the rate coefficient for the electron recombination on a linear scale. And H3+ is really a molecule where we can see all the features. So here there's a really broad peak at high energy spanning several electron volts. This is a direct DR process, where an electron is captured immediately into this dissociative state. For H3+, this dissociative state doesn't cross at low energy, and therefore people believed for a long time that it wouldn't recombine at low energy. But it actually does. As you can see here, it really goes up and up and up, and this is all the indirect process. So here the electron is captured first into a vibration excited state, and then it coupled to a dissociative state. And as you can see here in this plot, this is really the low energy here. What we're trying to measure in our experiments, and what's relevant for interstellar space, is the intricacies here of these really high rise at low energy, where we have to have a high resolution to try to understand all the details in this very sharp rise. So the first thing we worried about was vibrational excitation again. So we did a Coulomb explosion measurement like we did for HD+, for H3+, and what we saw there is that initially we have a relatively broad distribution in the storage ring that narrows down then, and after 2 seconds we have this distribution that agrees perfectly with wave functions that were calculated by Jonathan Tennyson, which essentially means that after 2 seconds of storage we're through with vibrations. We don't have to worry about them anymore, but now we have to worry about rotations. That's one thing that came out of these measurements too. Now the rotations to analyze those, we have a different technique. What we use there is we create the electron capture here in the electron target, and then we look at the distances of the particles on the detector after electron capture, and we can use this case of H3+, the 3-body breakup, where it breaks up into 3 ground state atoms, as a diagnostics for the initial energy that's in the molecule. So what we do there is essentially we look at the distance of all 3 particles squared, and if we, in this channel here, because there's no degree of freedom in the product, if we would have a ground state H3+ molecule, we would expect a kinetic energy release of 4.8 eV. So if you would get a 3-dimensional measurement of these distances, the sum of them would correspond to a peak at 4.8 eV. That would mean we have a ground state molecular ion in the storage ring. But the problem is usually we don't measure, and for this setup we don't measure all 3 dimensions. we only measure in 2 dimensions, only transfers here, and then this all smears out, goes all the way to 0, because the molecule can be aligned such that the atoms more or less hit the same spot. So then we get a picture like that. And then we also have to deal with the fact that we don't have a point source, but that our electron cooler here has an extended length, and therefore it smears out a little bit here at the end. But eventually it still means that that the end of our distribution, or the middle here of the distribution, should be lying at this 4.8 eV. And that would be a diagnostic if we really have ground state H3+ in the storage. So when we do these measurements and try to use this imaging approach as a thermometer, what we saw is these were the experimental results here, the dots with H3+, using it from a standard ion source. And then we did a simulation of what it should look like if we had ground state H3+, and that looked like this. So we clearly have a shift here. We also have a tail. The molecule is not cold. And in order to fit the molecule with a rotational distribution, we had to put in something like 3000 Kelvin. And that distribution that stayed there for the whole time, we measured for up to 2 minutes, and there was no change essentially. So we had long-lived rotational states that we had to get rid of. Now we different approaches were devised then to try to do that. We came up with cold ion sources. There were 2 different approaches. There was first only expansion source that was used at cryo together with a group from Berkeley, and we decided to go for a 22-pole ion trap where we would pre-trap the ions, cool them with a buffer gas, and then inject them into the storage ring. And as you can see here, the situation now is greatly improved. If you compare that to a normal standard ion source, we are pretty much lying on that cold curve. And when we saw that for the first time, we were really happy. We thought we have 10 Kelvin ions, but we should have been more careful because there is a deviation still. If you want to plot that on a logarithmic scale, these ions are not ground state, rotational ground state. This is really at the limit of our resolution. If one looks at it very, very carefully and just fits, it turns out that the ions are more like 300 Kelvin, which is a great improvement over 3000 Kelvin, but not what we need for interstellar space. Nevertheless, the R spectrum that we can achieve with these ion sources, these are 2 different measurements. One is from TSR, these are the black dots, and then there's a cryo measuring, also with a cold ion source, what we believe is a cold ion source. You can see they agree for the first time quite well over the entire range. We also see all these structures that had been absent before. But the biggest improvement over our understanding has happened in the meantime in theory, where Slava and Chris for the first time managed to have a really 3-dimensional representation of the dissociation process and produce a rate coefficient that is in the right order of magnitude and doesn't agree too badly. As you can see, the theory is more structured than our experiment, and that is something that we're currently trying to understand. Now, these are the most detailed comparisons to theory that have been done very recently in our group together with Chris. Here you can see the calculation for 300 Kelvin, which we believe is round about what we have in the storage ring. These are the storage ring data, and this is the calculation. And as you can see, the agreement here is not too bad actually in this region here. But if you go to really low energies, we still have a problem here. But you can see the storage ring data have peaks here that are not well represented by the theory. And as of today, we don't know what it comes from. What's also shown here are the rotational thresholds. These agree with the theoretical prediction, but in our storage ring measurements, we don't see any of that. And right now, it's not clear what the reason for that is. We don't know whether we're thermal in the storage ring. We don't know what kind of states we have in there, and or whether still the theory has to be fine-tuned. So that is going on. Also, another interesting development in theory has been the simplified approaches here. This is a very nice paper from Jungmann and Pratt, where you can see that it's now possible with an analytical approach to reproduce the overall size of the rate coefficient up until the first vibrational state that opens here and get pretty much the right number. I think that is a very, very promising approach, especially if one considers that we cannot measure in detail every single molecule, and maybe we also cannot calculate it in all detail. If we can find a reliable, simplified approach, that would be very nice for interstellar models, for example. Okay, another thing, maybe I should keep that short. Another thing that we can do is we can provide information on the dissociation dynamics of H3+, where we again use this fragmentation technique, and we look at the energy sharing, the momentum sharing between the molecular ions. Here you can see what's called a Dalitz plot, and it represents the different geometries in the breakup. So here you can see that we have a clear peak at linear breakups, although the molecule is a triangle, which you can clearly see when we look at the Coulomb explosion result, where we measure the shape of the molecular ion in the storage ring. We clearly peak at an equilateral triangular shape, but the breakup then actually happens in the linear configuration. So that's additional information that we can also provide. Okay, the battle rages right now with H3+ at the final frontier, so to speak, at the state-specific measurements between the lowest rotational states that we would like to do at some point in the future. These states have different nuclear spin symmetry. One of them is an ortho state, the other one is a para state. And in interstellar space that's important because we can observe these two different states and find out whether they're thermal or not. Right now, theory predicts, the latest theory predicts that there is a huge difference between ortho and para at really low energy. About an order of magnitude, the para state should be recombining faster. And that is supported actually by afterglow measurements that have been done very recently, where they see an enhancement in a helium-argon hydrogen plasma in the recombination for para H3+, while also H3+ seems to be much slower. In the storage rings, we didn't see this effect. We also tried to do this measurement here, where we used different para-ortho mixtures diluted with argon, and we saw a slight difference between ortho and para. If we extrapolate that difference to 100% ortho and para H3+, we see a very interesting spectrum here. We can see that sometimes the trend goes up. We see very, kind of a lot of details here, but we definitely do not see that large difference, especially because the rate coefficient then merges at higher energies, and if we do thermal rate coefficient, the difference is very small between the two. But we also have to admit that our measurements might not be cold enough. We just might not be in the range yet where the ortho and para states separate. This is a problem for interstellar space because if one looks at the observations and compares H2 and H3+, what we would expect, this is a curve that compares the ortho and para ratios of H2 and H3+, and we would expect them to lie on the thermal curve here. And the point where they would be lying on the thermal curve would give us the temperature. So this would be 60 Kelvin, this would be 30 Kelvin. But the problem is that H2 agrees kind of with what we believe is the temperature of the cloud. If we extrapolate that down here, we're getting about 60 Kelvin, but H3+ seems to be much colder. That is weird, because they collide with each other all the time. So what we have is, we have an excess of para H3+, and that is very, very difficult to explain, especially if we take into account the previous theory that says para H3+ should recombine much faster. If we do that, we get no way to reproduce these data here. If we put in that they are approximately similar, so we can try to understand these things. So that's another problem that you have trying to reproduce interstellar observations. Okay, now I want to switch to a somewhat more complicated molecule. This is H3O+. H3O+ is important because it's on the pathway to create water in interstellar space. The water formation in the gas phase happens like this. H3+ reacts with an oxygen atom, forms OH+, and then in successive hydrogen abstraction reactions we form H3O+, and then in electron recombination we get H2O. This process has been studied a number of times. What's especially important is the branching ratio between these two states here. It is typically around 0.25 or 0.15. And so the reaction can go different pathways. It's a source of water in cold molecular clouds, and it also might be the source of emission coming from comets. So here we've used, to get the branching threshold, what has been used is a very new detector here. It's a semiconductor detector that has energy resolution and spatial resolution, so we can get the kinetic energy release out of it. We can get the branching thresholds all at the same time. Typically, branching thresholds have been measured with grid methods in front of MCPs. That's been something that's been used very successfully at cryo-ing. But this detector here, that's a development of Henry Brewer and others, has been used to measure everything at the same time. And what we can see here is 3 different product channels here. And what we would expect in the kinetic energy release, the maximum in these channels is given by the end of this arrow here. But what we actually see is a distribution that's much lower. That means all the kinetic energy release that's available doesn't seem to go into the molecule, which also means that this product gets probably very highly excited. So we get really hot water out of this reaction, and that's also important for interstellar space. For the next channel, the same is the case. We also see much less kinetic energy release than would be possible, so this OD also seems to be excited. But even more puzzling, in the 3rd channel, we see much more than there should be in the system, which means that this ion, even now, even in the storage ring after more than 20 seconds of storage, is still rotationally hot. Even H3O+ is at a temperature of around 3000 Kelvin. So in the future, if you really want to have a measurement that is relevant for interstellar space, we need colder ions, and especially we need much better control of our ions. And that lets me switch over to the new experiment that we want to do in the future. This is the CSR cryogenic storage ring. It's an electrostatic storage ring that Richard has just introduced so nicely. So this is a 35-meter storage ring. So in that sense, my storage ring is bigger than yours, but then again, you have 2 of them, right? But so this storage ring is going to be cooled down to temperatures below 10 Kelvin. The entire lattice here, the interior chamber is cooled down below 10 Kelvin. And the reason for that is that we want to make sure that even hydrogen sticks to the wall. So we have dedicated spots that will be cooled down to 2 Kelvin for active cryopumping, and we have a platform that will go up to 300 kilo electron volts. So for the entire storage room will be equipped with different gadgets here. Of course, we will have an electron cooler again. That will be the new thing. There hasn't been an electrostatic storage room with an electron cooler because one needs relatively high energies. Otherwise, the electrons get too slow. So this storage ring will go up to 300 keV, 300 kilo electron volts, and that means the electrons are still fast enough for efficient electron cooling. So what we could do with a storage ring like that, for example, if one goes back to HD+, here these are the measurements at 300 Kelvin, and this is a prediction from theory. If one would go to 10 Kelvin, one would have only J equals 0, one would get this really sharp peak here. And the question is, will we be able to see that? So by going from 300 Kelvin, one gets rid of all the rotational states. At 10 Kelvin, one essentially gets only J equals 0, and a little bit of J. This storage ring has been under construction for a few years now. The outer vacuum chambers are all standing as we're talking now, and one of the corners has been assembled so far and cooled down. It takes about a month. We have reached temperatures below 10 Kelvin in this section here, and we also have a prototype where we can store. We have an electron beam trap where we can store an ion beam for several hours if need be, and have a vacuum on the order of 10 to the minus 13, 10 to the minus 14 millibar. That means the proof of principle operation has been demonstrated, and now we're essentially putting together the other 3 corners, and we hope to be done with that in about half a year from now. This is the interior chamber. You cannot just cool down a chamber easily, even not in this insulation vacuum here. Therefore, we have several layers of super insulation in between that, an onion-shaped design, and it's relatively difficult to choose all the materials that will work at 10 Kelvin, 2 Kelvin, and 300 Kelvin, because we also have to be able to heat the storage ring. Actually, most of the parts will go down up even to 600 Kelvin. The electron cooler is a somewhat tricky design, because at these low energies it's very hard to do electron cooling, and this is really the achievement of Andreas Wolf together with co-workers to design an electron cooler that can still work at these low energies. What one needs for that is, what we want to be able to do is we want to be able to cool electrons that have a mass of 100, cool ions efficiently at least, that have a mass of about 160 atomic units. And in order to do that, we need very slow electrons. This is something like 500 kilometers per second, which seems fast on terrestrial standards. But for electrons, this is very, very slow, much slower than what we used to do. We hope to go down to 1 electron volt with the electron cooler, which does not mean that the collision energy. The collision energy will be on the milli-electron volt scale again, but the electron beam actually has to be as slow as 1 electron. In order to do so, it is this time much more complicated to couple the electron beam into the storage ring. One needs this relatively complicated magnetic design here, not to perturb the molecular ion beam too much so that it gets thrown out of the storage ring. Okay, here's what I would like to call the roadmap, what we would like to do, what kind of experiments we would like to do in the near future. We will start off, of course, for the DR measurements with relatively simple molecular ions. Again, HD+ is on our list. We want to see if the ions really get cold. Possibly helium H+, it has a large dipole moment. Then a special molecular ion, I believe, could be CH+, because for CH+, we actually know that we can dissociate it with a laser easily inside the storage ring, has a high rate, and we can label all these states. This has been done in the TSR, and we got this spectrum here can be reproduced perfectly at 300 Kelvin. So we understand every single peak. If you would cool this ion down to 10 Kelvin, only the J equals 0 should be left, and you have a perfect thermometer. And therefore, that would be, for example, to do comparisons to theory, that would be a very good molecule, because then we could, in the storage ring, show that we really have only 1 or 2 rotational states. Okay, then come simple polyatomic ions like these one, HNO+, N2H+. Then come what I like to call the special ones. Our pet molecule Hc+, of course, we still have to deal with that problem. It's still not over. A special role there might be D2H+, because if you want to do this detailed comparison with theory, it will be hard in the beginning at least to really show that we have only rotational ground state of Hc+. We don't have a viable laser spectroscopy scheme for that, although we're working on it. But for D2H+, we would be pretty sure that couples strongly to the radiation fields. There we would be sure that it will thermalize after a few minutes or so. So if you could do detailed calculations on D2H+, and you would be able to store it for 10 minutes in DDR, we'd be pretty sure that we would have only the lowest rotational states. And then we could do a benchmark measurement, compare to theory, and then see what we can do for H3+. And of course, H3O+ is also on the list because of the water formation that we'd really like to understand at lowest temperature. Then we would go to more complex molecules, and here essentially the sky is the limit, because the storage ring doesn't have a mass limitation anymore, so essentially electrons should be going on the same trajectory as DNA or something like that. Protonated methanol is again a candidate that has been measured before, and other more complex molecules. Okay, I want to use 2 more minutes to make an advertisement for another project that's not really related to the DR measurement. We also want to be able to study ion-atom collisions in the storage ring, so I'm in the process of creating a neutral beamline, second platform here. This is a large source platform. This will have kind of a whole railroad system connected with different ion sources on there, go up to 300 kilovolt. We're in the process of building a second platform that will be able to produce negative ion beams, and then we can photo-detach them here and produce a neutral beam that goes all the way through the storage ring. And then we will be able to study very important reactions that haven't been studied yet, something like the deuterium fractionation with atomic deuterium, hydrogen charge transfer, low energies have been studied, carbon chemistry, the formation of CH+, atomic carbon beams have never been studied so far, and this whole gas phase formation of water process here, H2 plus oxygen, we should be able to study. The other reactions here we can study in ion traps, and then we can have the electron recombination. Essentially we can follow the entire water production in the gas phase here in the near future. And this is just another scheme, another reaction scheme, where we are sitting with ion-atom collisions at these really crucial points that lead to water formation, organic chemistry, and all these things. So we hope that with this new instrument in the near future, we can go into a kind of a next generation set of experiments, because in interstellar space, the molecular ions, they're really having a renaissance right now with these new instruments coming up, Herschel and ALMA, and we hope that with CSR we can also bring these collision physics into the next generation. So, and this is the group that I have to acknowledge. Of course, this is a larger endeavor. The storage ring is being built in the division of stored and cooled ions. Klaus Baum is the director here. Andreas Wolf is really the leading scientist of the storage ring, and also the expert for electron cooling. I've been lucky to just receive a European research grant to do interstellar relevant molecules, so I'm starting with my own research group right now. Money came 2 months ago, so we're only 2 so far, but we're growing hopefully soon. And then we have a number of external collaborators that are long-term collaborators. I didn't even put all the names of theoreticians down here. I'm only talking about the experimental collaborators here. So we have a group from Gießen that's working on atomic recombination. Of course, we need very special detectors for this storage ring. We're looking at the microcalorimeter right now that's developed in Heidelberg. And then we have a collaboration with Columbia University. And for the imaging, we're working with Xavier Aubin. And there is a long-standing collaboration with the Weizmann Institute of Science in Phoenix. And with that, I'll thank you.
From an astrochemistry perspective, how much is the gas phase formation of water relative to sort of formation of water on grains?
Well, that depends very much on the environment. Eric would be the expert there. Water formation on grains is incorporated in many of the models, but not in all of them, depending on the environment.
Yeah, it depends on the environment. In a cold, dense cloud, it's mostly on surfaces of ice. Infrared studies of ice show hundreds of monolayers on the grains. So much more. So, depends. And it also at high temperatures, they're neutral reactions. So
That's right, yeah.
Yeah, so it does depend on the conditions.
But I mean, for your recent model for the orthopower H2O plus, you used only gas phase on the other hand, right?
That's right. That's right. That was for H2O plus.
H2O.
Okay.
I noticed that your chain for forming H3O plus, or maybe it was D3O plus, didn't include the reaction I thought would be most important, which is water plus H3 plus. Or I thought that would be one of the most important things. Is there some reason that is not the dominant path?
That's a good question. I mean, one of the things is that, I mean, the Herschel observations, the new ones, have found surprisingly little water actually in the gas phase. There's a whole mission, there's a WISH mission that was dedicated to detect water in star-forming regions. In the beginning, they had a hard time finding water, but by now they have found it. There's a surprisingly large amount of H2O plus and OH plus, and that is not understood right now, because it's believed that H2O plus and OH plus react with H2 immediately, and if these molecules are there has to be H2. So right now it's not clear how that comes about, why they don't react, and whether this chain is really the gas phase chain. So H2O plus, you're saying H2O plus H3 plus. Now that's certainly something one could look into. Yeah, I don't know. Does it contribute? Do you think it's an important aspect, the H2O plus H3 plus? No, H2O plus H3 plus.
No, I'm sorry, I'm a little lost. The
Yeah.
OH plus and H2O plus,
Yeah.
it depends on what the conditions are. In diffuse
That's right.
clouds, there isn't that much H2, presumably. So that doesn't destroy them, but in dense clouds, and where they're seen, there's also a very strong radiation field. So they're photodissociation processes that lead to them.
Yeah, but Chris' question was like whether H2O and H3 plus is an important formation route for H3O plus.
Yeah.
Yeah. Okay. So it is. Yeah. Other questions?
So you gave a very nice list of things you want to DR on. Can you get cooling functions to these things, either vibrational or rotational, particularly for the diatomics?
You think can we measure them?
Yes.
I think so. I mean, as you recall, for H3 plus, we were able to,
Yeah.
confirm your measurement. I think for the first time on an absolute scale. Right? I mean, the
Yeah.
vibration lifetimes we got there. I think we should be able to do that. So what we eventually want to do is really be able to measure rotational state specific inside the storage ring, so that we probably later excitation or dissociations. And for CH plus, for example, that's not a problem. For other molecules, H3 plus is difficult, for example. But other molecular ions might be possible.
So for CH plus, for instance, we've calculated rotational cooling or excitation rates, which are quite important.
Just radiated forms or with electrons?
No, with electrons.
With electrons.
With electrons.
If that is,
These are used in certain regions in the interstellar medium
I see.
for models, and basically there's no experimental confirmation of what we calculate whatsoever. Very nice situation for theorists to be in, but
I see.
probably not the healthiest scientifically.
I think
So
for
it'd be
CH
nice
plus
if you could
yeah.
actually,
I think for CH plus we should be able to do that. Yeah.
Okay.
Because there we have a clear route to do diagnostics on an error.
perhaps we should talk about that.
Yeah, that's a good point.
Other questions?